So let's go ahead and get started. And congrats! I mean, this is it. This is our final go around here. And as I mentioned, I do like to kind of spend some time and talk about where we've come and where we have to go still, and possible progress we can still make. But I think in the interest of our time collectively, how we best want to use our time, just in this compressed semester we have. I'll just really leave it at this point here, and I won't spend any more time kind of wistfully looking back at the whole semester and what we've learned. But and it may not be for a couple of weeks, as you take this break we have upcoming here, that you can look back and think back to your knowledge base and your skill set, um, back in August, and where it's come now. And it took a grind to get there. There's no doubt. And I said on day one, I wasn't trying to scare anyone. It was just a reflection of reality that we're building a processor in this class, and you really can't cheap out on that. You have to put the time in to do that, and to understand why certain things are the way they are. And that's really the important point of this course. Very few of you are going to be graduating and moving on to a role where you're designing CPU pipelines. Very few, maybe two in total of this 150 students in this class. But understanding the why of computer architecture, I think, will pay very big dividends for you in your industry careers. Even if you're much higher up on the abstraction levels of computing, knowing what's happening underneath the hood, I think will be very beneficial to all of you. And I do hear back from former students who say that. So I'm going to skip all of this. What's real? What else you could learn after this? Let's ignore all that. Um, where to go from here? Yada yada yada. That's all important, but I think in the interest of time, those notes are available. It's not on the exam, so you don't have to. We don't have to cover that. So on to the exam, and I think I've mentioned enough of this that nothing I'm saying should be a surprise to anyone. But I just want to make sure our bases are covered here. Our exam is Saturday. That is tomorrow. It's at 7:30 a.m. It's from 7:30 a.m. to 9:30 a.m. This question has come up many, many times, the extent to which the exams are comprehensive. My answer is always yes, but that doesn't mean that it is covering, MIPS programming like you would have seen on exam one, or single cycle processor modification and ALU design like you saw on exam two. The expectation is, while we do kind of make these checkpoints along the way, everything has been really building upon each other. I think we can really only appreciate caches, for example, even though it seems like a somewhat tangential topic, we can really only appreciate what they're doing with our understanding of what's happening at the assembly level, right? And likewise with our understanding of why it's so critical for our pipeline to be full of data and why those caches are necessary. So that's what I mean by comprehensive. We are 100% going to be focusing on what we've covered since the last checkpoint. If you recall, last checkpoint, we had started talking about pipelines. We had gotten to the laundry analogies, but no further by the previous checkpoint. And I said, don't worry about laundry, um, for that second exam that we had. And we didn't have any questions. Our questions were limited to understanding critical path for single cycle processors and ALU design and things like that. We've everything since then is what is our fair game. And in terms of our actual topics, if you look back on the class schedule in Canvas, that corresponds to the lectures um, 8 through 11, through essentially Wednesday, although we didn't really get to a lot of what was in that Wednesday topic. And the textbook also is equivalent sections. It's really the entirety of the textbook in the sense, but really, primarily, it's those chapters 4 and 5. And I don't think there should be any surprise. The question is always fair to ask as you're studying and desperately cramming tonight. Do we need to know chapter 4.11? There's no surprises, in my opinion. So if you're reading 4.11 and it doesn't connect at all to anything we've done this semester, it's not going to be on the exam either. I'm not going to be throwing trick questions that, oh, did you actually read that section? And that's what this question is going to be about. Every question is based on what we've been doing in class, both what I've been talking about, and we've had 70 classes this semester, right? So what I've been talking about, what we've been doing for our quizzes, and what we've been doing for our homework questions, and then what we've been learning through the lab process, but not any lab specific questions about how do you stall this pipeline register in VH. That's never been on the exams, and it won't be on the exam tomorrow. But it should be based on what we've been discussing. So I will say, and history does prove this out. Those of you who are here today, not necessarily in person, those of you who are watching today and are regularly watching, are at a huge advantage. When it comes to the exam. Um, you can read those questions in my voice, and that's what I'm going for with those questions. They're not meant to be trick questions. Um, they're meant to be based on what I think we've covered, and I do look at every question, and I look at them more than once, and I say, you know, is someone who's been engaged in this class and has done the homework and has not just copied answers from elsewhere and has actually put thought into what they've been doing in this class. Do they know what I'm talking about in this question? That doesn't mean you get 100% on it, but you should do fairly well on the exam when that's the case. Likewise, lengthwise, and we talked about this already, it's of similar length to exam one and exam two. It'd be a tight 50-minute exam, but you have 120 minutes. So to me, that means you have plenty of time to make a first pass through the entire exam, and you have, if you choose to use your time in such a way, a time to take a second pass and think about questions a little bit more deeply and add more nuance. I've also made almost all the questions those short answer, provide me your thoughts type questions. So it's not about making sure you get the exact number of 2.75 and then Canvas auto grades it or not. That's probably best for both of us in terms of total exam grading time, in terms of your stress levels while taking the exam. Little caveat: I mentioned 5 questions. It's 5 questions, but Canvas separates the sub questions. So in Canvas, it shows up as 10, but it's I think of it as 5 questions, five topics that those questions are covering on the exam. There's just sub points on those questions, which Canvas calls them separate questions in Canvas. So conceptual knowledge is all from this last 1/3 of the semester. It's a little bit less than 1/3, but we started kind of slowly this semester. So really those last like 4.5 weeks is what it's really included. Um, these are all just very rhetorical knowledge based questions. None of these would be exam questions. This is the knowledge base. I would expect you to just kind of know. That's me snapping my fingers. I have my camera turned off. I would expect you just to kind of know, um, without having to like think about it terribly deeply. With understanding that this you could write a few sentences about each one if you needed to, but none of these should be questions where like, well, I have no idea what this question's even about. And so that's what I want you to think about when I list these kind of conceptual knowledge questions. These aren't exam questions. These are, what do I expect based on this last third of the semester? What are kind of the big picture points that I think we have covered? Um, so, for example, when I ask, what is the CPI of an ideal pipeline processor? You could actually write a page about that if you wanted to. At least I would expect you to be able to talk quite a bit about that. But for us, our big picture takeaway has been we've been building this scalar pipeline, right? That's in contrast to pipelines in which you're trying to fetch multiple instructions at once and maybe interleave multiple threads and things like that. We're not doing that this semester. We haven't built that. We haven't learned that. For our ideal pipeline processor, our ideal CPI is 1. We want in the steady state to get every instruction done in a cycle. And what prevents us from that is all the things we spent a lot of time on. You didn't get to build it in the lab. For most of you, I would think you didn't get to that part of project part C, and that's okay this semester. But what prevents our CPI of 1 is all the dependencies, all the potential hazards we have in our pipeline. The easiest way to think about it without having to worry about the precise dependency of, is it a load followed by a store or not? Does that cause a one cycle stall or not? Just think of control hazards to start with. Every time I have a branch, I have this instruction in which I have incomplete information to execute it in time. I don't know if that branch is going to be taken or not. I consequently run the risk of fetching instructions that I shouldn't have. That's going to cause my CPI to increase, and usually in a measurable way. Right, based on 100 instructions, 12 of them are branches, and for 12 of those branches, 50% of them we predict incorrect. I'm wasting 6 cycles out of what could have been my ideal CPI, and I can do the math and get a CPI of 1.06 instead of 1.0 for that instruction mix. So that's why I say you can write a page about all of these. The answer is always it depends, but we've gotten to the point this semester that it depends on things that we could very clearly should be able to state. And that's what I mean by these kind of conceptual questions. What is the ideal speed up from pipelining? I think that's an important big picture concept. This applies to anything that we pipeline. This could apply to software pipelines. Is for 480, there's a lot of talking about the graphics rendering pipeline, OpenGL pipelines, DirectX pipelines. Those do not exactly correspond to our pipeline processor, although they can, corresponding to a pipeline set of operations, like our laundry and our assembly line pipelines and all that, right? The big picture takeaway was our ideal speed up from that was a function of the number of stages we can have in parallel. How much we can subdivide the work and have parallel things operating on the work at a time. So for an n stage pipeline processor, our ideal speed up is n. But we know a lot of things potentially limit that ideal. First off, it's very hard to cut into n equal pieces. It's just hard, right? From a circuit perspective, it's hard. You've built these functional units, and you can subdivide and subdivide until eventually you have to cut one of those subunits in half, and that becomes tricky, right? And it's just hard to balance things exactly perfectly. And likewise, not just that issue of splitting up your critical path equally, for our pipeline processor, it's all these other issues. The longer you make your pipeline, the more life gets complicated. Your ideal is still really great, which is a speed up of n because you've kept your CPI at 1 while increasing your clock frequency by a factor of n. That's our ideal, but our reality is the longer it gets, the messier it gets, the more edge cases basically you have to watch out for, and the more extra logic you have to throw in, and that's fundamentally limiting what your performance increase can be from pipelining. So that's what I mean by these kind of conceptual knowledge questions. You should be fluent in these topics. I didn't, but I could ask you on the exam to write an essay about any of these topics, or a one paragraph essay about any of these topics. What are the three kinds of data dependencies? I think we covered that pretty well. At least we spent about 15 minutes in class. We had a quiz where everyone seemed to do okay on the quiz question for that one. But we have the three flavors of data dependencies, of which we really just care about. There's four. Yeah, you're right. I know. As I was saying that, there's four. We really just care about the read after write dependencies. Yes, I appreciate you said that. There are four kinds of data dependencies. Um, yeah. We care about primarily for our processor. We care just about the read after write data dependencies because for our processor and the type of ordering of our instructions and the potential hazards that come up, it only really comes up in the context of reads not happening after the writes that they're supposed to. But there's the other kinds. For any pair of instructions that are using the same register, that is a dependency of some sort. We can talk about to what extent do we care about the dependency. That's a separate question. These instructions are 10,000 cycles apart from each other. Do I care whether there's a dependency or not? The answer is probably not. The dependency is still there. So the types we have refer to the read and write operations. So you have read after read, which we usually don't care about. If you reorder a read to be before that read, it's fine, right? We've read something and we read it in a different order, but we didn't change our processor state in any way that breaks something. So read after reads are reads after fine. Read after reads are fine. Write after writes are potentially a problem. But for our processor, it just so happens that every instruction writes at the very end of the instruction. So it doesn't lead to pipelining issues for us. There are other processor designs that have varying cycle length instructions that could cause a problem for, but for our MIPS, we don't have to worry about write after write hazards. And for the write after read hazards, because our writes always happen at the very end also, we never have a circumstance where an instruction reads or does the write operation after it was supposed to do the read operation. So it never happens in a backwards manner with that style of dependency. So for us, there's multiple flavors of dependency. We should be able to spot them out. Anytime there's a pair where register T1 is used twice in a code segment, that is a dependency. You can label it as such. You should be able to do it fairly quickly as well. Which ones do we care about? Well, we care about the read after write dependencies. A slightly compatible question to that is, which ones do we really care about from a performance perspective? Which of those read after write dependencies are ones that we cannot resolve via forwarding mechanisms? That's our load use dependencies. And so you're looking for some patterns when you're observing a block of MIPS code. You're looking for read after write dependencies primarily because that's going to trigger your forwarding logic. And you want to make sure you're testing your forwarding logic and your forwarding logic does what it needs to do. You're also really looking out for those load instructions. So when you see a load in the code example, it's there for a reason. It's there because watch out, if there's a use case immediately afterwards, for our MIPS 5-cycle implementation, we're going to have to stall a cycle. So it's a very common question. It was in our homework as well. Can you reorder instructions to prevent that from happening? And similarly with regard to our branch instructions, we know when we see a branch, we potentially have an issue. There are certain approaches, both in terms of software scheduled pipelines, which you built in the lab, and we also have as a legitimate approach to building a pipeline, and hardware managed solutions. So for our software scheduled solutions, we have this concept of a branch delay slot, which basically is saying your branch is being determined in cycle 2. So that next instruction is potentially inerrant, an errant instruction that shouldn't have been fetched. The software scheduling approach to that is what you're kind of doing in the lab, right? Which is, okay, because I don't have good branch prediction logic or anything of that nature, let's just assume that the next instruction is always going to be executed. That's our branch delay slot. And I'm going to put something in there that I otherwise would want to be before the branch or be always executed no matter whether the branch was taken or not. If we can't find something useful, then we put in a no op. And we're no worse off than if we flushed that next instruction anyway. That's our software managed solution. So when we refer to a branch delay slot, it's a checkbox in Mars, right? That's assume the next thing is always executed after the branch. But then there's our hazard detection logic. We have a branch. If the branch got taken, we need to flush that PC plus 4 instruction. Those are two complementary approaches. You would be doing one or the other. And an exam question would be talking about one approach or the other. Can you put something valid here? That's your branch delay slot. Or you're going to have to stall. That's your hazard detection. Analyze the code and determine what you can do in either of those circumstances or what the performance would be in either of those circumstances. And finally, although it did probably feel like a bit of a break when we switched over to caches, that was our final topic. That's what we just really finished up on Wednesday. And caches are all about locality, right? So the big picture of caches are all about locality and understanding that we're making this trade-off between the size of our storage and how efficiently or how fast we can access data inside that storage. And that's what our memory hierarchy, that kind of triangle picture, right, is. You have relatively small, relatively fast storage as close to the data path in your processor as possible. You can think of your register file as a cache, as we've talked about. And then you have successively larger and successively slower layers of cache that allow us to help to guarantee that we don't have to continue going to those further away layers of memory storage. But there's that trade-off involved. So you have tiny caches, relatively tiny caches very close to the pipeline. And then you have successively larger and slower caches further away from the pipeline. That's that memory hierarchy. And we've talked enough, I think, about how the term cache is a relative term. We're always caching data. There's copies of data in many, many places in our hardware, in our software, across the network. As we're accessing real applications and real data, our cache in computer architecture terms is referring to that hardware managed, usually SRAM transistor based structure in which we have to store some metadata in the cache to be able to reliably access the right data that may or may not be in our cache at any given time. So the big picture is locality. Caches work because of temporal and spatial locality, and we've had homework questions now about identifying each. That's an important big picture. To take advantage of spatial locality, now we have to have a cache that is storing more than one element at a time. That's our block size parameter that we have here. And I think of it as by making our cache block wider, by making our cache fatter, we're allowing us to store not just A of I, but also potentially A of I plus 1 and A of I plus 2 and etc. And that's what allows for our spatial locality. But by their very nature, they take advantage and exploit temporal locality, right? We put something in there. We've only put it in the cache because we expect to be able to access again in the future. That's temporal locality. That's why a cache exists. Spatial locality is this nice thing we can also hopefully take advantage of by storing nearby things as well in our cache. And then in terms of where we really spent a lot of our time over the last 2 weeks as a class, it was a lot of that. You can think of it as cache arithmetic or address bookkeeping with regards to how a main memory address breaks down into the constituent components. Homework 11 was optional, but you should take a look at it in terms of if you need more prep material, do homework 11. I do expect that the questions are phrased such that you have that fluency. That if I say you have a direct map cache where 8 bits are for the index field and 4 bits are for the offset field, you should be able to tell me everything I need to know about that cache. And you should be able to trace that cache for a series of accesses, which is a homework 11 style question. I think it's fair game. You know, it'd be more fair if we had 2 more weeks, to do this and to go over it even more slowly and have more homework and more examples. Well, it's still fair game. So I do. You should expect that style of question in a couple different versions, but it almost always breaks down to from a text description of what the cache is to an address mapping, and then from an address mapping, we should be able to trace exactly what's happening as addresses come in our cache, or vice versa, from an address mapping to what the cache actually is. You should be able to do both because they're an equivalent sort of representation. So you should be good with your powers of two, and knowing that 4 bits means 2 to the 4 things we're accessing, and that picture of the set associative cache that we had in class that we brought up a few times. I prefer the architectural layout versus the kind of logical layout of it. That is your best bet, I think. At least for me, if I'm working on this exam. And I do recommend even having a pencil and paper handy while you take the exam tomorrow. It's not required. But when tracing cache, I think we were seeing that we were better off when we were circling the right bits of the addresses as they were coming in, and as we were kind of roughly drawing out what was happening in the cache. Canvas versus a pencil and paper exam Canvas doesn't let me have you do that very easily. You should be doing it anyway. You don't have to upload it or anything, but just as you're working through the problems, having pencil and paper handy is going to be a good use of your time, and you do have the time to do that. You're not going to be scrambling tomorrow. And that's what these kind of conceptual questions. I think we did not cover average memory access time at all. So that one it's not hard, but we can't do it at all because we did not even talk about it. But the rest of this we did cover. In terms of having split instruction and data caches, we didn't talk a lot about it. We did talk enough, I think, about write policies, both the write through versus write back caches, as well as write miss policies. But at least write through versus write back is something I think we covered well enough. And we could talk about we talked about the trade-offs involved in those two possible policies. Let's jump into some so-called what I call rejected exam questions. I think I've hinted at this before. I call them rejected exam questions, but they are former exam questions, and they're rejected now. I do reuse exam questions, as some of you have discovered, but I do reject some over time if I find there's something that isn't quite right for a 381 final exam. This one was rejected. Maybe 5% too difficult is why I rejected this question. So you may in fact see a version of this question that is 5% easier than this version. It's asking you to do a lot. There's no doubt about it. You have the time to do it on the exam. So we talk about comprehensive questions. This is a pretty comprehensive question. Day one of this semester, I think you have no idea how to answer this question, presumably, right? And only in understanding that connection between C and our ISA and our assembly mapping, and now our cache mapping, can you even get started on a question like this? So I think this would be a good one to spend a little bit of time on. Maybe we won't go the entire way through, but let's make some progress on this one, and I'll just walk you through my thought process for working on a question like this. There's a few things going on here. So we start with that it's a triply nested loop, which that's pretty ugly. But the main consideration is we have this array, this grid of data of 4 by 6. And we could draw that out, logically what that means is a data structure where we have 4 rows and 6 columns of our data, and this is 0, 0, right? I'm not gonna be able to draw them all, but that would be, 0, 5 right here. And then you have the next row and the next row and the next row after that. That's our logical data structure. That's our, human programmer view of what's happening in data. Our computer architect's view, though, is understanding that what? Our main memory is just a linear array of bytes. Our main memory is not two-dimensional or three-dimensional. Our main memory doesn't have physically linked lists or anything like that, right? Our main memory is just an array of bytes. And if I've helped you with anything to become a better, developer at the end of the semester, hopefully just remembering that you should never. I believe you should never struggle with a pointer problem again after this class. You'll still have them. You still have seg faults and things like that, but you should not be mystified by them anymore. I would think after this class, pointer, just an address. We're calculating an address. Did I calculate it right or did I calculate it wrong? And if you do it wrong, the compiler or runtime will tell you pretty quickly. But we know that that two-dimensional data structure is just an abstraction, and ultimately it is just an array of bytes in memory, and it's a linear array. I could draw it vertically. Let's just draw it horizontally for space here. That at some base address, which is the pointer for grid, which is alias to grid's name there, we have 0, 0, followed by 0, 1. And let's draw 0, 5 here. And then that is immediately followed by 1, 0. That's our layout. That's our row major order. That's how all semester. Let's make sure I got the right final value here. That's how all semester we've been doing our load word and store word array arithmetic to go from C code down to our underlying pointers in our memory, our addresses in our memory. That is our layout of grid. And to answer this question, you have to know that. It doesn't necessarily matter which address it corresponds to, and there's a little bit of ambiguity in the question. You can answer it slightly differently and still get full credit, but you have to know that it's laid out like that. I use the hint that it's in row major order. That's not a necessary hint. It's kind of our default assumption, but it's laid out row by row by row. So within that starting context for this question, we have this outer loop. This outer loop, if I were to add a comment for that outer loop, it would be do the main code enough times so that we get a good answer for our cache hit rate. It's not there to do anything. It's just repeating what's in those innermost loops there. So n isn't given. That shouldn't trip you up. N is large, we assume. It's there so that we get the correct number back out by just counting it enough times. So how many misses do you see is then going to be a function of n, or it could be thought of as a percentage as well. Either answer would be perfectly fine. And then all we have is a loop that just goes element by element and does a read. I know we have a few, I'll call them hyperliteral students, and actually, you may not realize that I appreciate you very much. Even when you fight me on things, I very much appreciate you because you make me really think about the assumptions that are baked into questions and how they can be misinterpreted. So this one, the assumption is read is doing some read of that location of memory. What else it's doing, we don't know. So the assumption I was making with that phrasing of the question that you should be making is we're doing load words. The question is the same if it's store word. We'll get to the answer here in just a second. Yeah. But it's accessing whatever it's doing. It doesn't matter. It's doing something. It's grabbing each value of that grid array, and we're doing that whole loop enough times with k from 0 to n that we should be able to get a steady state kind of answer here. Finally, we get to the cache part of this question, right? So if we're assuming a direct map cache of 64 bytes with 4 word blocks, you gotta be a little careful, right? We've used the term correctly and consistently throughout the semester. You would have to let me know if you wanted to make this assumption differently. We're assuming 4 word blocks, and our word size is our integer size. So 4 entries of grid fit in every single block. That makes our life a little bit easier. We don't have to worry about, in this case, we don't have to worry about the actual physical address mapping. We don't have to trace it at that level to answer this question. But what it says is we have a direct map cache that stores 64 bytes with 4-word blocks. That is, in my somewhat biased opinion, that is enough information to answer this question. And I do think it helps to draw at a very high level what that cache looks like. It's not going to look like much. 64 total bytes. That's 16 words with 4 word blocks. In terms of the data in this cache, and we can actually kind of ignore the make that larger. That's correct. It's just a little small. In terms of the data in our cache, it's going to be a 4 by 4 grid. Isn't it nice that on the very final day of the semester, I finally figured out how to draw in PowerPoint without messing it up every time? Okay, 4 rows. That's not the right term, but I've been using it throughout this semester, throughout this topic. 4 indices into the cache, right? Direct map. So there's 4 rows in the cache, and each of those has 4 words. So 4 columns of the cache. You need to know that to be able to answer this question. Otherwise, you're just guessing. 4 word blocks. That's 16 byte blocks, and there's 64 total bytes in the cache. That's why there's 4 of those rows. And that's why this is not a tricky question. It does require some thought in terms of how many misses that you see. We start off, we're going to access grid of 0, 0. And just, in the interests of space, I'll just draw G00 here. That corresponds to grid of 0, 0. We're going to do that first access, and that's going to be a miss. I spoke too soon. That's going to be a miss, right? Because the cache is empty. The cache started. You were actually very close, Nicholas. So just to make you feel a little bit better, if you would explain your assumptions, which you'll have space and time to do, and walk through what you were trying to figure out, you could get a lot of points for that question, right? So it's not an all or nothing question. Only I believe one of the questions on the exam is an all or nothing question in terms of your understanding. That's going to be a miss to start with. I'll tag this as a miss. We have to be a little bit careful because that's only a miss the first time potentially we access it. But this is a 4-word block. The whole point of having that is we do have that miss, but we grab in its neighbors. So when we go and we're going on our J loop here, that's a miss followed by 3 hits. We're unfortunately going to have to walk all the way through this to answer this question properly. If you had said 75%, or that's misses, if you had said, 25% miss rate, I'd still want to see a bit more to give you full credit for this question because there is a bit more to it. But it's obviously pretty close. What happens next? We do G00, 01, 02, 03, 04 comes in. There's no doubt and there's no question as to where it actually is going. It's going to go next. You can map out the actual lower order address bits if you needed to, but it's that next thing. That's how our direct map cache works. We have the index bits, and they're going to be increasing in memory because our 2-dimensional layout of our grid data structure is just an array of bytes, right? It's pointers that are incrementing as we go. That would be a miss, though. It wasn't in the cache when we first wanted it. The nice thing about accessing thing in this IJ type of pattern in our code is we bring in G05 and we actually do bring in G10 because it's whatever's next in our address space, which happens to be, because of how this code is written, exactly what we want. So let's just walk the rest of the way through this very quickly. This class may take a few hours if we're not careful. I'll record it all, so we won't stop the clock here. That's the same pattern again: miss followed by hit, hit, hit. G20, G21, did I screw this up? Let's double check. That's 6. That's 1, 2. That's 6. Yeah, it's fine. Followed by this G23. Same pattern: miss, hit, hit, hit. The problem, as I see it next, or the steady state of this code is going to show us, well, what happens next? We want to request G24. It has to go in the cache. it would presumably alias back to what was here. And then that pattern would continue. You would be writing over the top. Exactly right. So the answer is, 25% miss rate. You could, as long as you explain what you're talking about, there's lots of possible valid answers. It's a function of n technically. You could actually count the number. It's, there's 24 times n total accesses. So there are 6n misses. That's the technically correct answer, but 25% would also be fine. Because that cache is smaller than our grid size, we're going to continue to keep moving things around as we go. We're never going to get that second hit from a block. If that grid size was 4, 4, well, then we'd be golden, right? That first time through, there'd be misses on each block, and then it'd be hits indefinitely, right, for n. But that's not the case here. Because our grid is larger than our cache size, um, it's going to continue to miss and only hit on the successive 3 attempts we have here. So this is a cache that exploits spatial locality pretty well, but doesn't actually exploit temporal locality at all. Even though the application has a ton of temporal locality. Yeah, if you made int 1 byte, and this is why I talk about literal students and how I appreciate all of you. Int has a very clear definition in the C standard. We don't look at the standards and how they've evolved over time. Int has a guaranteed minimum size, but it could be quite larger as well. So we have been using ints as words as 4 bytes all semester. So that has been my default assumption. But I understand that as well. Always, certainly on an exam, it's always the case in homeworks as well. It's always fair game to state your assumptions and try to describe your thought process when answering the question. And state your assumptions and write clearly. That's always a fair game. Now, if my assumptions are that magical unicorns make this a 100% hit rate, I'm not going to give you credit for that. That's a valid question. Let's just follow the entire example then. I'm going to do it in my head or just out loud versus writing it down. Let's just follow it all the way out. 2 4 2 5 3 0 3 1 3 2 3 3 3 4 3 5. Very good. Okay, that's absolutely correct. So let's do that then. Let me finish the entire question since I did it very quickly and slightly wrongly here. Let's continue and finish the entire example. I probably would have given you full credit for 3/4 anyway because I just came up with that answer. Appreciate it. Let's do the entire loop. G of 2 4 is going to be a miss followed by 3 hits. Same with the next row. But what I neglected at the time, that I really appreciate you all. Hey, by the way, that's great that you caught that. What happens next? There is no 4 0. That's what I did when I was very quickly just walking through it in my head there. It ends. The array is over. There is no entry 4 comma 0. It's 3 5 is the last entry in this array, right? So what would be next in our loop would not be accessing 4 0, which is not here. It'd be accessing 0 0 again. So 0 0 doesn't magically go here all of a sudden. This is a direct map cache. If 0 0 was here before, 0 0 would be here again. Still a miss, followed by, let's walk all the way through it now that I got it wrong. I feel very obligated to do that. We're seeing that repetition, and that makes sense because it's the same axis as being repeated over. But what happens, and that was the point being made in the chat here. By the way, that makes me feel great that you caught that. Well, I feel terrible that I got it wrong, but I feel great that you caught that. Still at our 25% miss rate, but what actually happens now, right, is G1, 2 through G2, 3 didn't get overridden in the cache. Yeah, what would the actual mathematical expression would be? Let's do it in terms of percentage. I think that's the easiest way to do it. We know there's 24 axes, so n is part of the equation, but it's not that important. Yeah, well, I think that was the point of the question. Now that I think about it, 24 total axes times n, so 24n total axes. We know the first time through we miss on 6 of those axes, but every successive time through the loop we miss on 2 of those 24 axes. So yeah, technically you have the expression in terms of n, but I would say that's 2 over 24. 1/12 would be our miss rate for this cache. Let me reflect on this for a moment. Well, that's why we have partial credit. You'll be fine. Um, we're going to skip the average memory access time question. I feel bad about it. You'd be able to do it, but we didn't cover it, so that's too bad. So skipping that one entirely. I kind of thought we would get to it. So this is a question we definitely did. We have to state our assumptions with this type of question. I'm seeing some. Let's go back just for a second. I'm seeing some more discussion with regards to what people are thinking. Why wouldn't G04 right over the G00? Um, they have the same index, but they have some like arbitrary programmer index, but their addresses would be increasing in memory. So it's whatever the address corresponds to, and it gets laid out row by row by row. Um, okay, so for this, I wish we had a few more weeks this semester. Okay. Um, wouldn't you miss 6 the first time through, and then 4 every subsequent time through? Um, okay, so there's 24. Let's do that math one more time. I believe our tracing is completely correct, but there are 24 axes through these two loops here. Again, k is just there to give us a steady state answer. You can or the k loop is there to give us that steady state answer. You can calculate precisely in terms of n, or we can assume n is very large, which gives us what our average would be. The first time through that loop, we miss on 1/4 of our axes. I'll fight you on that, right? 1/4 of our axes, because we have a miss and then we grab the next 3 elements. Always. So it should be a miss followed by 3 hits. So you would miss 6 times the first time through the cache. That would be 1/4 of the time. So that'd be six misses and 18 hits. And then afterwards, you're right that we're actually just gaining 2 more misses turning into hits the next time through the loop. So that would be 4 misses and 20 hits. Well, I said it was a rejected exam question for being slightly too difficult. Everyone gets partial credit. Let's move on. Okay, so I'm appreciating what I'm hearing there. Is that you are looking at it at that level of depth, and you're seeing it. I think we were correct as we're tracing through the cache. The general process here is correct. We just actually calculating that out, what that works out to be. I believe that's correct. The only two we're still missing twice in these elements here because they're overriding each other each time. But now here, it's really just these 2 misses. The second and nth to the nth time through the loop become hits. So it's still every time through that loop, it's still always 24 loads. That doesn't change. We're removing the first time through, we have a 1/4 miss rate. Every subsequent time through, then we've gotten rid of only 2 of those misses, not half of those misses. We've gotten rid of only 2 of those misses, and that gives us a 1/6 miss rate the second time through. We didn't have it. Okay. We must move on. All of our math was off. So that's fine. State your assumptions, walk through, don't just write, 7 for that answer, right? That's when you're disadvantaged relative to your peers. State your assumptions, walk your way through the problem. Um, I give a lot of credit when I can for logical reasoning process, even because we all make mistakes along the way, certainly in the time pressures of an exam or in an exam review session. So I would usually not ask you on the exam to indicate all the dependencies in the code below. It's fair to do so, but it's annoying. You'll waste minutes making sure you didn't accidentally miss one. So I will ask something like indicate 6 dependencies in the code below, just so that you know you're done and can move on, because asking for all is slightly unfair on an exam. Um, but that's what this is asking. Let's do just a few of them. So indicate all the dependencies in the code below. We know that our dependencies, certainly the ones that we care about, are the ones that are those read after write dependencies. So you do need to continue to be aware of where the reads and where the writes are for these instructions. The writes are the first one. The destination register is that first one. And we talk about comprehensiveness of the exam, cumulativeness of the exam. You got to know that. I guess I could phrase it slightly differently, but you have to remember that. So I don't even recommend you have a copy of the green card in front of you. You don't need it for this exam, because my expectation is that much and are pretty fluent in it. And a lot of you didn't believe me in week one when I said, "Oh yeah, you'll be able to look at this and know this code and know exactly what's happening." But I think we're there, right? I mean, just in the process of testing your processors. So there's a lot of dependencies there. The ones we care about primarily in terms of impacts on our pipeline are those read after write dependencies, of which there are a number of them in this code base here, right? So that's T0 read after write dependency. That's a T1 read after write dependency. Um, I did not auto grade this question because it too much ambiguity. So you'll just have a chance. You'll have a chance to say it in text exactly where the dependencies are. You'll everyone will be able to get full credit on this question. How's that for optimism? The one that you may miss in terms of read after write dependencies, because it just looks a little different, would be this last one here, right? It's a little unfortunate, but it's the truth that store word reads from two registers. This looks like it's a write, but it's not. It's a read. Because store writes write to memory, which is a cache issue potentially. But in terms of dependencies in our pipeline, we read to register T2 to write it to the yes. It'll be a little bit. It's a little bit better than this on the exam. You'll say label 1 has a dependency on register 2. There'll be a format for it. I think that question will turn out okay on the exam, and it's not auto graded. That'll be okay tomorrow, I think. Um, okay for you at least to grade to do the work. So that last one though is a valid one, and I would say if you missed that, and if I asked you for all the read after write dependencies, you'd lose a point, for that particular question. So that's the first part. Identify all the dependencies. We have modified that question slightly to instead identify all the read after write dependencies, and I'm looking for people to tell me that I missed some because I love you guys, and we did. These are usually ones we don't care about in terms of read after write dependencies, uh, but it's there. And technically, there's a read after write dependency there as well. Um, it's phrased better than that on the exam tomorrow. That there's very specific ones that we're looking for on the exam tomorrow. But fine, those are all the dependencies, read after write dependencies, I believe. Technically, how technical you want to get. This is a read after write dependency, right? Even in the same instruction, but we're usually referring to dependencies between instructions. We read from a value in one instruction, we write to it in a subsequent or vice versa instruction. So the second part of the question is the more important one, I think. So we identify the dependencies. How many stalls does one iteration of the above loop incur? Does the one iteration of the above loop incur? Assume branches are resolved in the decode stage. So this question doesn't say anything about there being, a valid branch delay slot that we can fill something meaningful there. It's asking how many stalls. There's a lot of different potential things that are stalls. The first thing we always want to look for when the question is asking about stalls is those read after write load use hazards. Our MIPS pipeline processor can't handle those. We The question would say, assume I think the phrasing I tend to use is assume the traditional or the textbook approaches to data forwarding and branch target address calculation. So that would assume yes. Assume that you got your Project Part C processor fully working, and that's the processor that this is being run on, where you can handle all those other data dependencies without incurring a stall. But this one we can't handle. We just don't have a mechanism that allows us to do that much forwarding via a hardware mechanism. So that would be one we would look for. And the way this question is phrased in this particular version, where each time we go through that branch, we only determine whether that branch is taken or not in cycle 2. So for one iteration of the loop, there's certainly going to be this stall, and we have to watch out for this stall as well. Another way to phrase this type of question, it was like this on homework a couple weeks ago, and it'll be like this tomorrow as well, is how many um, how many cycles does this code take? I've totally lost the plot here in terms of time. What I will do is we'll keep going a little bit longer until I run out of energy here today. It's all recorded. I understand that many of you have to go. I will have this entirely recorded and uploaded so that if you're missing it, I don't want to cut us short here. Let's do a little bit more together. Um, if you have to go though, I won't take it personally because I understand you have other things going on and classes going on. Later today, as this is posted to YouTube, play it back at like 5x speed, and then maybe you'll skip over my mistakes and only get to the correct answers at the end. So another way to phrase this question though is how many cycles does this take from start to finish? That's a slightly different, not meant to be a tricky question, but it's slightly different question than asking about the number of stalls. And the only thing I'd say to watch out for that is there is this issue of it takes time to fill the pipeline. Even going back to our laundry analogy, right? It takes time to fill that pipeline, and potentially, it takes time to flush out the pipeline, to empty out the pipeline after that last instruction. But don't double count that. In terms of our bookkeeping of total number of cycles, you either count that latency for the first instruction, or you count it for that last instruction. You don't count it for both, right? There's not separately a time to fill and a time to empty the pipeline. There's a time to fill because to start with, if we assume the pipeline is empty, this first sub instruction is not done in one cycle, right? If it's an empty pipeline, that first sub instruction feels the full latency, and we pay for that full latency of that one. This one is not done until cycle 5. Until cycle 5. That's a 5. Cycle 5. There you go. That one's not done until cycle 5. And then our pipeline's full. So then we have our nice, okay, everything is CPI equals 1, CPI equals 1, CPI equals 1. I think to be precise, I would say that our stall cycle is felt by this instruction, not the load instruction itself, right? The load continues as is. It's that next instruction that has the actual stall associated with it. So that one is not CPI equals 1. That one technically has an extra cycle. We don't measure the CPI of individual instructions, but as a whole, we've increased our CPI by 1 there. 11. And I would argue that through the loop, that's 12, 13. If we're going back, or it's just 12 if we don't take the branch. Depending on how the question's phrased, your answer is going to take one or both of those. Those 5 cycles to fill up is not a stall. It's just the latency of getting started. That you have an empty pipeline, and that add instruction or that sub instruction is the first one here. Takes 5 cycles to get done. So if the question is asking, and it'll be more precise than that tomorrow, how many cycles does it take to run this entire block of code, assuming an empty pipeline? You would have to start with calculate the time it takes to fill the pipeline. What I was getting at is don't double count it. Don't assume that this now takes 5 more cycles to finish, because no, that's already kind of baked into this. We say this, is done at either cycle 12 or cycle 13 here, depending on the branch issue. But that's assuming it got fetched back in cycle 8, right? So you don't double count those latency cycles. They're already kind of baked into this equation because we're fetching 1 cycle per instruction. This first one's not done until cycle 5. But cycle 1, it's fetched. Cycle 2, this is fetched. 3, 4, the fetching happens much earlier than that. So that latency is only felt by that first instruction. And that would be the perfect way to calculate total number of cycles here. So that we talk about rejected exam questions. That one was rejected because I said the word all on there, and I get it. Somebody said, I spent 30 minutes on just this question, and it was meant to be a 3-minute question because they were triple, quadruple checking that they had every single possible circumstance there. And so all is never a great thing to phrase it. So it'll be like 6 or 7. It'll say tomorrow. Here's another rejected exam question. There's just a lot going on a paper exam, I think I'd feel okay asking this exact question because I would lay out the caches or give you space to lay out the caches. It's very similar to a homework 11 question if you want to look at a slightly more longer version of that same question. So it asks about a 16 byte cache. So that is a constant. So a 16 byte cache and our access string, right? Our access patterns there. It's asking to work a little bit backwards, which is for that access pattern for that particular cache, can you get the result that is being shown here? And I would ask you to defend that answer. Can it do that or not? Let's do it for example 1 and example 2 here. I think in the interest of time, it's just more of the same for the other ones. So let's do it for those first 2 examples there. So the first one is we have 4 byte blocks with a 2-way set associative cache. So I still suggest we draw that out, that we have 4 byte blocks and a 2-way set associative cache. So 4 byte, 2-way set associative with 2 sets of 2 blocks each. And that's a nice little hint there. I would literally draw it as such. That is way 0, and this would be way 1. So for each of the following cache configurations, explain whether it can produce this sequence. I don't really think there's a way to answer this without attempting to trace that sequence yourself. That's my opinion here. So for that first one, we get address 0 comes in, and it misses in that cache. That would always be the case. We assume the caches are empty to begin with, so we have a miss. We can map this out to our binary arithmetic if we want to. You could probably answer the question without it, but let's start with that binary mapping. So we would potentially need to look at a 5th bit here, but I don't think we will. But that's a 6 bit for that one. So we have our 4 or 5 bit encoding of those addresses to begin with, where byte accesses are happening here. So these are byte loads, and we have 4 byte blocks. So for that first cache, and the nice thing is for the next one, it's also 4 byte blocks. We know that these 2 least significant bits, I'm going to try to draw it all the way through here, are going to be our byte offset. We did okay. And for this 2-way set associative cache, we have 2 total blocks each. And that would just be the next bit for our index. Whew, we got it. We have that address mapping. Walking through what happens in the cache is just referring back to that for every access here and filling in our little cache layout, our abstracted layout that we have here. 0 comes in. 0 is a miss. We know exactly where 0 goes in the cache. Technically, we don't know, does it go in the left way or the right way, but it doesn't really matter. It goes in either one. Depending on how the question is phrased, I would certainly tell you if that's the case. But we know what also goes in that cache. Location 0 goes in this cache, as does, based on our address mapping here, 1, 2, and 3. Okay. Next comes up, and it's 12. 12, the tag bit's relevant but not super important for us right now because we're writing the whole address in the cache right now anyway. 12 would also, of course, be a miss in the cache. And because the index is 1, we would put, again, it doesn't necessarily matter if it's left or right as long as we're consistent. 12, 13, 14, 15. The nice thing about these addresses is both for 0 and 12, they're 0, 0. So there's no guessing. We know exactly which location is happening in the cache. So far, the question is asking whether that first cache can do this one. No, of course. I mean, all the caches are going to be misses on those based on their current description. Will there be a hit on location 1? Looks like it. It's there. So you're getting to the meat of the question now, right? Is what happens on when we have some repeats later on. So 17 comes in. Where does 17 go in the cache? Can someone tell me? Well, yes, but where exactly in the next set of blocks? The 0 or 1? Top of the left. Top of the right. Thank you. Second way, first block. Or yeah, we have to be a little bit careful here. Maybe we write our index fields here so it's clear which one's which. This one, right? And we have to be a little bit careful now in terms of what gets put in there because that's our block offset of 1. So it's not 17, 18, 19, 20. It's 16, 17, 18, 19. And I think if that's not clear to you, I mean, that's okay, but that's something for you to review. Because the block address corresponds to that location, and that entire set of addresses would have the same exact block address. 16, 17, 18, 19 would go in there, even though it's 17 is all we've requested. Next comes in 15. Could that be a hit? Absolutely. Could 3 be a miss? There doesn't appear to be a miss possibility for 3. There's no reason we have evicted it from the cache. So we know, in fact, for that first cache here, it's asking 2 questions, but the nice thing is we only have to ask the first one. Explain whether it can produce this sequence. No. You have to explain for it to be a good answer, but the answer is no. It can't produce that sequence because there's no reason for us to have evicted 3 out of this cache for that access pattern. That would have been a hit for this particular cache. Let's do the next one as well. The odds of me making a mistake as I do this live grows exponentially as we do more examples, but let's just do the next one as well. 4 byte blocks that is direct mapped. So it's similar, but it's a slightly skinnier looking cache, right? So it's a grid. Still, it's 16 blocks. Still it's 4 blocks either way. But now there's no set associativity to worry about. So, this is going to look kind of bad here. The main difference now, our block offset's still exactly the same for this cache. What's different in terms of our address mapping for this cache? Between the example 1 there and now this example 2, this direct mapped version. Oh, it wasn't a rhetorical question. Give me your thoughts on this. So we go from the two-way set associated where there's 2 sets of 2 blocks each. Now we just have 1 set of 4 blocks. Yes, we now need. That's great, Augusto. Thank you. We now need an extra bit for that block index. I mean, we kind of see that, right? There's 4 things now, 4 rows, 4 indices in our cache. We need an extra bit. So now we have to be a little bit careful because it's going to look sloppy. And I'll try to draw it this way, where now we're looking at these 2 next significant bits for our cache address. Gotta be a little careful with our sloppiness here. It may have been better to draw it out. The 2 least significant bits are still our block offset. That doesn't change. The next 2 bits are our index. So that's going to change how we lay out things in the cache. And so we should potentially get a different answer. So if this answer is for cache 1, now our answer for cache 2, we start off with a miss, of course. 0, 1, 2, 3. So far, so good. We look at 12. 12 definitely goes somewhere different in the cache, right? Now it's index 1, 1. 12 is going to go here. So far, so good. Address 1 comes in. It's there. 17 comes in. And we have the same issue as before because that doesn't change with regards to our byte offsets. 15 comes in. It's a hit. 3 comes in. It's a miss. No reason to believe that that cache can reproduce that pattern as well. I think we have to do the last one, don't we? Let's do the last. Let's do example 3 here. We never got to an example that couldn't do this. 8 byte blocks that is direct mapped. Sure. Yep. What was I looking at to see otherwise? I must have been looking at 15. Thank you. Let's get back to where we were here. Who was that wise, mysterious voice? Thank you. 0. We put in 12. We check 1. Not thank you. Okay, great. We're looking at these two middle bits for 17. Looking at these two middle bits for 17, which is 0, 0 again. So what now happens in that cache is this is where our 16, 17, 18, 19 goes. So that's a miss. Still correct that it was a miss, but now where it's put in the cache is different. Thank you. 15 is a hit for the same reason as before, and now we can produce this pattern, right? Because now 3 is not in the cache. We don't really have to even update the cache to answer this question, but yeah, technically now the cache does get updated again. And we know this is going to be a miss because 7 was never in the cache at any point, but we would see that 7 would go here. We can fill in that block accordingly. Let's do this part 3 of this question as well. Just sounds like you guys have it, but let's do this part 3 of this question since we're all here together. We have 8 byte blocks that it's also direct mapped. That is now a shorter, fatter cache. It is the Zambrino of caches. Okay, where we have just 2 blocks. So we're back to what we had before, the block 0 and a block 1. I'm going to be a little bit then more careful now with our breakdown of bytes in our block here. 4, 5, 6, 7, and there you go. There's our 8. And I think it may be helpful to even lay out, now that we have so many so we don't lose track of them, what that corresponds to in terms of our block offset. Thank you. No, other people cannot see through my head. Was that you thought that was just your screen? Okay, thank you. No, keeping my head there. Okay, thank you. Getting a little punchy at the end of the semester here. All right, direct map cache with 8 byte blocks that is, has just 2 blocks here. So now we're going back to our address fields, and I feel like I'm going to redraw them because it's getting way too messy to see what's happening here. I said that for these cache questions, pencil and paper, obviously not PowerPoint and tablet pen, is definitely the way to go as you're tracing these things out. Let's do them again. The addresses. Okay. Okay. We know what we need to know based on this question. We are again going to only have 1 bit for the index, and now we're going to have 3 bits for that block offset because we have 8 byte blocks. So in terms of that breakdown, it's those least significant 3 bits are relevant to us, and it's really just that next bit is what we're using for that index. So that upper order bit for the tag for 17, it's still relevant, it's still important because we're putting the entire address in the cache to show what's happening here. We don't really need to know that information, but it's there for us. So we have the 3 least significant bits are our offset, and it's only that 4th bit now is what's our index into this direct map cache. let's walk through the pattern again. So we start with 0. It's going to be a miss, obviously. And the nice thing about that axis pattern is we know exactly what goes in for this direct map cache, the rest of the block. 12 comes in, and we can see where that's going to go. I can definitely see where this gets confusing. I mean, the nice thing is we know, just like in that grid example, it's going to kind of keep going forward in memory. Or you can look at the block offset and it'll tell you as well, right? 100 is our block offset. We know that's where 12 is going in that block. So we can, in fact, you can work backwards and do it that way, or you can just assume that it's the sequential addresses. But either way, it gets you the same result, which is 8 through 15 going to that next block in the cache. 1 is a hit, looking good. Now we're back to that 17 miss again here, right? 17 is a miss, and somewhat similar to before, it's going to overwrite that 0th block. So, this is where life gets a little messy again, but let's draw it out here. So there's our 16, 17, 18, etc. And I think that makes sense in terms of what's there because, again, the first 8 bytes went here, the next 8 bytes went there, the next 8 bytes are going to have to go back here. There's nowhere else to put them in the cache, right? The cache isn't big enough for our purposes. We do that access. Can we get a hit on 15? Yes. Can we get a hit on 3? Yes. And then I'm not going to draw it all out. For this one, is 7 going to be a hit or a miss? There we go. 2 people said it's a hit. They must be right. And they are. Because when we missed on 3, we'd put this entire block back in, right? I'm just not going to draw the whole thing. We'd put that entire block back in. And so it would be there now available for us in that particular cache. Again, I wish the entire class was here, to be honest. So I want you to be thinking of my voice when you're answering the questions tomorrow. It's the same style of questions. I'll call that one rejected also because there's just a lot going on with that particular question. Let's do this final one, and then we will say our goodbyes for the semester. I promised I wouldn't cry. I'm not going to. Okay. So, there is going to be a question of this style. It's a little bit trickier for me to ask it on this Canvas exam because I normally like for you to just, draw on top of the diagram and show how things would be working. And we can't do that. So you have to really just explain as best you can what is happening here. There is a version of this question tomorrow. So, consider the data path below with some forwarding logic, but no hazard detection units. Which of those code fragments will execute correctly with the following data path? It's a little tricky only because it's showing you kind of an incomplete version of your kind of textbook version of these that picture of these slides. But you can trace, and it's even kind of highlighted accordingly what that forwarding unit is doing, right? It is taking values from 2 different possible places, right? It's taking a value from the output of that EXMEM register and potentially forwarding it. And it depends on how you like to look at these kind of things. Certainly when you're designing it in the lab, as well as just understanding the homework questions associated with it. Do you prefer to look at it in terms of the muxes as driving everything, or looking at the forwarding unit, or just looking at those data path units and tracing those? At least the nice thing is we know for this example, and the color coding does help a little bit, that there's the kind of, you can call it like the conventional path through, right? This is nothing is getting forwarded. This is our regular processor data path operating as expected. That's input 0 to those muxes. Again, in our non-pipeline processor, those muxes aren't even there at all, right? We don't need those muxes. And then we have 2 possible forwarding paths, right? And 2 different signals to dictate separately whether forward A is happening or whether forward B is happening here. It doesn't exactly say, which value corresponds to which one, but I don't think we need to know that to be able to answer that question because we look at where the paths are actually coming from. And we can see one of the paths is coming straight from here. You want to draw this little layout here. straight from our ALU output back into those muxes. And then the second forwarding path is on our write back path. Straight from the output of technically that mux, but that write back mux that we have here, back to that forwarding path that we have there. So the question is, it could be thought of a couple different ways. Which of the following code fragments will execute correctly with the forwarding data path? You look at the first code fragment, the one on the left here, right? That's a read after write dependency again between the destination register of that source instruction and the RS register, first source operand of that consuming instruction that we have here to answer this question whether or not it can be forwarded. Now, you could answer this by just saying, yeah, we know we can handle this via forwarding. Well, this question's asking specifically because it's more likely to fail than just add. Yeah. Okay. So yes, you can answer the question. Yeah, based on what I know, this one on the right is a stall, and this one on the left is not a stall. That is technically correct. The question is going to ask you to look at a specific pipeline implementation and answer that question. So you have to be a little bit careful. If I ask you the question instead, for my conventional textbook pipeline processor with all the project part C stuff put in place, what happens in this code? That's a much easier question, potentially, right? Yes, the one on the left we handle via forwarding, the one on the right we have to have a stall. And so this question is asking you, well, what happens? And the answer is it's wrong, right? The data would be incorrect on the one on the right versus the one on the left because it is a data dependency. And we talk about how this requires a stall, but there's nothing in here to actually make it stall. It doesn't magically stall just because it needs to. It needs to have that logic that detects that circumstance and actually instantiate the generate the right stall signals to make sure the instruction, the add instruction doesn't continue. The reason this question can become a little bit tricky is because I may be possibly providing you with a data path that has certain aspects of these paths in place. So to answer the question, because of how I've phrased this one and because of how I phrase it tomorrow, you actually do want to trace it through. Don't just assume, yeah, based on what the textbook tells me, one on the left is fine and the one on the right is not fine. So take that into consideration to begin with. So we do want to confirm and we do want to check that for this one on the left that our forwarding logic does work, and it looks like it should because it is checking those values. It is checking the right control signal, that we're getting the register RD signal, and we're presumably comparing it to both our RS and our RT, and we need them both for this one, right? We're checking that the first source operand and the second source operand, are they equal to each other? And we would also technically have to check something that's not listed here in the diagram. And what would that be? There's another important signal that needs to come into this diagram. So it depends how literal you want to be. No, this forwarding logic is broken because it's missing something. We've lost the plot, and that's fine. We also need to make sure it's an actual read write. Yep. I don't think that was the crux of the question, but that's an important consideration you want to mention. Well, that forwarding logic is missing the read write signal. So would it actually work? It would accidentally work in this case because it assumes that every instruction is doing a read write, and so it doesn't have that signal. But you would generally want that to be the case. But then for the example on the right, which is our load, we know, I guess, that's a load use delay and that's a stall associated with it. So we know it's not going to work correctly. And so we can trace the paths and see what would happening. That there is a feedback path from the memory back into our ALU stage, our execution stage, but it happens one cycle too late. It's not going to work for our purposes. I think that's a good place for us to stop today. The semester has to end, so let's let the semester end. Tomorrow, have some fun with it. Explain yourself, defend your answers, state your assumptions, and you're going to do just fine. Those of you who've been here and who've been present, My goal is for those exams to be fine for you because you've done your part. You've been a good faith participant in the class this semester. Hey, it's been interesting. It's been an experience. I don't know what else to say about that. I hope to see many of you again, and I hope to see many of you in Coover at some point in the future. It's not going to be in spring semester, but I hope to see many of you again in the future. And you know, you're always welcome. Once I'm actually in my office to stop by and say hi and chat about how life is going. And and I hope that we get that opportunity at some point here. But otherwise, I know you gotta push for this final last part of this semester, this exam and finishing up various projects. Do your best with that. Put some real effort in. You're gonna be just fine. And I'll see everyone tomorrow. And then otherwise, I'll see everyone on the other side. So thanks.